Okay, so the following is our agenda. We are looking at the Lewis models, vsepr, which involves lone pairs and bond pairs, and which leads to a topic about molecular shape in particular, but also the contrast between electronic and molecular shapes of atoms, molecular being the more important of the two. And then formal charge. And finally, bond order, which is just missing off this agenda list. So bond order is the final thing that we need to look at there. The importance, of course, of molecular shapes being very relevant to, for instance, enzyme action and site specificity for the fit for enzymes, this idea of the lock and key hypothesis. So molecular shapes are really important, right down to the practical level. The example being given right now is enzyme action within the human body. I mean, at its simplest, the Lewis dot symbols, all that it really means is a symbolic representation of the valence electron. So that means, again, from the previous tutorial that we had, that we're looking at the outermost shell on the atom. Okay, and we're looking at the valence electrons, which means that there are electrons within this outer shell, but we're only interested in the outer electrons because these are the ones that are involved in bonding. So what we've got then is we've got the electrons on the outside, and we're going to make reference now to lone pairs and bond pairs. Okay, so if you look at another example of a Lewis dot symbol, we're looking at one down here. This is HCl, and we're looking at covalent bonding, but we're looking at the particular electrons that are encircling the chlorine and the hydrogen. So first of all, let's have a look at the lone pairs. So there you see it. You're looking at the lone pairs now, and so we're looking at one of the lone pairs. Around the chlorine there's actually 1, 2 and 3 lone pairs, and then between the hydrogen and this remaining electron, what we've got are what's called the bond pair. We'll have a look at that. And now we're looking at our bond pair. So those are the differences that we're essentially interested in when we're looking at the end of this, which is to predict molecular shapes and electronic shapes. And this is the kind of methodology we've got to look at. We have to look at lone pair electrons and bond pair electrons, because these influence the actual shape, the electronic shape and the molecular shape. Okay, so the important and really interesting difference between the lone pairs and the bond pairs is this: that the lone pairs, because they're not involved in any of the bonding between the two atoms, for instance the hydrogen and the chlorine, because they're not involved in the bonding, they actually fix themselves closer to the nucleus of the chlorine atom in this case. They're closer to the nucleus, that's the point. Now, because they're closer to the nucleus, they have a strong, their orbit around the nucleus is smaller, it's a smaller diameter or smaller orbit if you like, which means that these lone pairs, this lone pair and this lone pair and this lone pair right here, because they're in a smaller orbit, being like in charge, being negative in charge, being like in charge, they repel one another much more. Okay, so the lone pairs will repel one another quite a lot, relatively speaking, to the bond pair. Whereas the bond pair, because the electrons are being shared between one atom and the other, they're not as strongly affixed, if you like, to one atom or another. So their orbit would be greater, and they wouldn't repel the lone pairs as much. I mean, so to recap then, the lone pairs will repel each other a lot more than a lone pair will repel a bond pair. That's the essential point, and that has an influence on the shape of the overall atom then. The overall molecule, that is. Remember also that lone pairs and pairs of electrons are consistent with the sub-level model of electrons orbiting atoms, and it's got to do with this duality of two electrons, the spin up and the spin down. So this is consistent with having pairs of electrons. It's not unusual, it is consistent. Which then leads to the 6 basic shapes of molecular shapes, and the first one being a linear shape, and you can see you have your central atom and you've got your 2 terminal atoms. You've got an angular shape, same thing, central and 2 terminal atoms. Trigonal pyramidal is this example here. Trigonal planar, tetrahedral, and trigonal bipyramidal. So there are your basic shapes that you have for atoms, and there's an example then to the left of that of the electronic and the molecular shape. So we'll have a look at that right now in detail. The differences is in the basic shapes resulting from the different types of electron pairs. So if you have a bond pair and a bond pair, you get a linear shape, meaning that there's kind of equal repulsion, so you get a linear shape like that. If you've got an angular shape like this, for instance, then it probably means that, yes, these are 2 bond pairs here, but it may be the case that you've got a lone pair that exists up here that we're just not seeing in the molecular shape, but they do exist in the electronic shape, and that's why you've got this angular shape here. Even though you've still got 2 bond pairs here, there more than likely would be a lone pair of electrons up here, and they repel, as we know, they repel the bond pairs, and so you get this type of shape, etc. And this is how the others, even though they may be more complex, essentially that's how they have the different shapes. So here's a great example right here. We've got a molecular shape right here, which is trigonal pyramidal. Now, looking at it as it is, you might think, well, it should be trigonal planar, so why do we have a repulsion of the atoms, the grey atoms here, the 3 hydrogens in NH3? Why do we have repulsion downwards? Okay, well, that can be explained if you look at the electronic shape. What happens is that you've got a lone pair of electrons that actually exist in the electronic shape, and this lone pair here repels these atoms, the hydrogen atoms, so that they don't persist as a trigonal planar shape. They're repelled downwards by the lone pair. And that's why it's important to distinguish between the electronic shape and the molecular shape, because the molecular shape is explained by the electronic shape. And that's the essential point in that.